This is the Kinematics FRQ number 1. As usual, just try it on your own first. It's 13 minutes, so literally pace yourself. Like literally put on a timer for 13 minutes and get used to the pacing. I'm gonna go over it, and I haven't looked at like the right answers, so I could just be saying a bunch of wrong stuff. But hopefully you can correct me, and yeah, hopefully this all makes sense. So there's basically this cyclist. I drew it as a circle, and there's this ramp, and it's gonna go down the ramp and jump off and then land same height on the second ramp. And we got to figure out what is the horizontal distance in terms of the height, the theta, and the mass, like the mass of the person. So the way we would start is, well, just kinematics, right? I know that, here, I'll do it here. The distance traveled, we can use a kinematics equation. The distance traveled is going to be 1/2 acceleration times time squared plus v naught times time. So, a few things to just keep in mind. This is a projectile launch, like there's 2 dimensions here. We're going vertically and horizontally. So, if we think about, like if we draw the vector, right? If we draw sort of this right here, I'm going to try to draw it perfect. This is our velocity. There's always going to be that sort of Vx and Vy. And we know that Vx is really going to be what's causing the horizontal motion, I guess. Yeah, that's like the horizontal motion. So we want to put this all in terms of x's, right? Because we want to do like the acceleration. We want to do ax. We want to do velocity x. And if you remember, the Vx doesn't change, so we can, like the Vx stays constant throughout the motion because there's no like horizontal force that's, messing it up. What you really got to understand is that there's no acceleration. So we can actually just get rid of this whole term, because if we put in a 0, that just makes everything on that side 0. So we're just left with x initial equals v naught x times time. So let's actually just clean this up. V naught x times time. Okay, we don't want time in there, and we don't want v naught x at all. We actually just want height and mass and theta. So this actually is kind of tricky. We got to first deal with, we got to deal with both of them. Let's start with v naught x. We know that if we were to split up our components, so like this angle is equal to this angle, right? Because of, I don't know, the vertical, I don't know what you call it. Like it's a geometry thing. So Vx is just equal to V naught cosine theta times time. Okay, how do we get the initial velocity though? Or like, how do we get that, right? Because it's going down this ramp and there's a bunch of changing acceleration, right? This is where you use energy. So just because it's a kinematics FRQ, you can still use energy, whatever is in your toolbox, your physics toolbox, you can use that. So I know there's going to be no energy loss, so there's the E initial equals V final. And then we can set this this height where h is equal to 0. So at the end, there's only kinetic energy, because I set this is where h is equal to 0, so boom bada bing, there's no UG. And we have to now get the UG here, so we would do UG m naught g, and then we're going to use h naught, right? Because this is the height above h equals 0. And then we can just use 1/2 m naught v squared. This is our v naught squared, right? Because this is the speed that it's exiting. Masses cancel out. We're left with 2g h naught equals v naught squared. Alright? So, before I actually substitute that back in, because I can square root it and stuff, what I might, yeah, let's just square root. I'm going to treat this problem like I've never done it before. I'm just going to be like, okay, yeah, square root 2g h naught equals v naught. Let's just substitute that back in. Cosine theta times time. Okay, now we got to solve for time, because we don't know, like that's not in our equation. So we actually have to use a kinematics equation here. What's really nice is, remember, this is a projectile launch. So what you can do is you can actually realize that, okay, the time it takes to get from here to here is the same as the time it takes to get from here to here. And what I know is that initially there's Vy, right? There's a component of the velocity that's directed upwards, and at the sort of max apex, there's no Vy, right? Because it's not moving up. It's moving sideways, right? If we were to draw the velocity, it's moving this way, but it's not moving up or down. And then obviously once it starts curving down, it's going to start moving up. What we can say is that, okay, the Vy final is going to equal the Vy, I would say V naught V naught y, the initial Vy plus the Ay times time, the acceleration in the y direction. Well, this is actually going to be 0, right? This is going to be 0. And then we can put our V naught, and I'll actually write V naught sine theta, just as a reminder that we're dealing with trig and this is that component, plus accelerate. So, and then acceleration is just g, right? And for a projectile, its acceleration is, I'll say negative g. How about that? And I'll tell you why I'm doing negative g. Well, it's directed downwards, right? The acceleration is downwards, and it's equal to 9.8. Let's just solve for t now. V naught sine theta. Now, this is what you have to keep in mind. Remember, it takes half the time to get here, so I need to do t over 2. The full time, the t in this here, the full time is going to cross the distance. It's only going to take half the time, though, to get there, so I write t over 2, and then I just solve for t, so I get divided by negative g, divided by negative g, and then I'm going to have to multiply 2 by both sides. I get 2 v naught sine theta over g equals t. And then I can just substitute that back in. So, okay, x naught equals negative 2 g h naught cosine theta. And then we're going to have to multiply this whole thing by 2. My marker's dying here. I might switch to blue midway through. So 2 v naught. However, v naught is not in our derived equation. I can just use this v naught, right? Because it's the same velocity. Or same, it's the same initial velocity. The sine and cosine just decides if it's, the horizontal or the vertical. So we can use this and be like, okay, yeah, square root 2g h naught, and then what was it, sine theta over g. Okay, this is looking really nasty right now, but we can do some things to clean it up. I am pretty sure you could leave, if this was the FRQ, you could leave it like this. I would not recommend it because you'll see in the next question, it's probably not a good idea to leave it like this. But what we can do real quick, just clean it up, is say x naught is equal to, okay, when we're multiplying these two things, we have a square root and a square root. They're the same, they're the same square root. So if you multiply by itself, you're just going to get 2g h naught. Okay? So this times that, right? This square root times this square root, we get that. We have 2 times cosine theta times sine theta over g. And then you can see, oh, nice, the g's cancel out. That's pretty interesting because you can be on any planet, and now our equation will work regardless. That's pretty cool. Assuming I did everything right. But now we're gonna have 2 times h naught. Now, if you're in pre-calc honors, shout out to you because you can probably recognize this as 2 cosine theta sine theta. That's sine 2 theta. So yeah, there you go. That's your derived equation. I want to see how long that took. I think I was explaining it way too long. 9 minutes, not bad. But yeah, that's the equation. If you want, and let's say you're not in pre-calc honors, you didn't recognize that, it's totally okay if you left it as x naught equals 2, or like this 2 times 2, so 4 h naught cosine theta sine theta. That's cool too. But yeah, the next question just asks, like, okay, if the vertical distance was doubled, so instead of h naught, let's say it was 2h naught, then what would happen to the number of cars? All right, so, and then we can justify the equation using the expression of numbers. So it's just asking, like, how many more cars could you pass through? And we're assuming each car is sort of identical in width. So right now we're jumping over 6. So let's say this, here, I'll do it with black this time. This distance, let's say this distance, we'll call it x. I don't know, let's just call it x. So there's x, 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 right? All of these are the same, like horizontal distance. So we can say 6x. So 6 of the distance of each car, so I'll say like one car, is going to equal x naught. And this is just repeated addition. I'm literally just doing 6 times this equals the full distance. Now we derived an equation for the full distance. Like, this is our full distance. So if we subbed it in back here, it's just proportional reasoning. And I'm going to use a sine 2 theta version, but you'll find that no matter which one you use, it'll work out the same. Because now what we're going to do, we want to see what happens to the number of cars. Right now it's 6. And we're going to see what happens when we double the height. 2 times h naught sine 2 theta. So we double the height. We need to make these two equal. So we got to double the amount of cars that we go through. So therefore, 2 times 6, that would be 12 cars. So if you doubled your height, you would go through 12 instead of 6. So that's a pretty interesting question. That's pretty cool. Now we're just going to do a graph. So we're just sketching a graph of the vertical component. So the vertical component of the stunt cyclist velocity is a function of time, from like when it leaves the ramp to right before it lands on the second ramp. And then we're going to indicate like sort of component stuff. So yeah, let's just do it. So if we were to, I'll erase this stuff. If we were to graph vertical components and all that stuff, if we had something like this. So this is what they give you. So v, y versus time. Initially, the vy is pointing up. It's positive. There's vertical velocity. There's a vertical component. And then at the halfway point, as I mentioned, there's no vy, right? It's not moving up or down. It's just moving horizontally. So we know there's going to be no vy. And then, as it launches off, it'll have the same speed, right? It's going to have the same magnitude in a different direction, in the opposite direction. Let me make sure I do that right. So then if you were to connect it, yeah, that looks about right. So it would have the same vy if we were to draw this, but now it's pointing down, and that's just because the acceleration is the same. It's for the same time, therefore it's going to have the same velocity, just pointed downwards this time. So it's like a reflection. It's just perfectly, I don't know what you call it, like a reflection or whatever. Let's just draw some labels to indicate like what speed this is. So I wish I didn't erase that, but if you remember, we said 2 square root g times h naught is equal to v naught. So we can say that the speed in terms of all that stuff is just 2g h naught sine theta. And then for here it's the same speed but just negative 2h naught sine theta. So yeah, sorry if that video took too long. I wanted to just explain it thoroughly in case anyone had questions, because this is old stuff, so I think it would just be helpful to go through it slowly. So yeah, thank you for watching. See you on Monday.